Static routing. Exploring directly connected networks. As you can see in the figure, the show IP route command reveals the content of the routing table. Let's review the purpose of a routing table. A routing table is a data structure used to store routing information acquired from different sources. The main purpose of a routing table is to provide the router with paths to different destination networks. The routing table consists of a list of known network addresses, that is, those addresses that are directly connected, configured statically, and learned dynamically. R1 and R2 only have routes for directly connected networks. Observing routes as they are added to the routing table. We will now take a closer look at how directly connected routes are added to, and deleted from, the routing table. In contrast to show commands, debug commands can be used to monitor router operations in real time. The debug IP routing command will let us see any changes that the router performs when adding or removing routes. We will configure the interfaces on the R2 router and examine this process. First, we will enable debugging with the debug IP routing command so that we can see the directly connected networks as they are added to the routing table. Configuring the IP address and subnet mask. Next, we will configure the IP address and subnet mask for the fast Ethernet 00th interface on R2 and use the no shutdown command. Because the fast Ethernet interface connects to the 172.16.1.0/24 network, it must be configured with a host IP address for that network. After the no shutdown command is entered and the router determines that the interface and line protocol are in the up and up state, the debug output shows R2 adding this directly connected network to the routing table. The routing table now shows the route for the directly connected network 172.16.1.0/24, as seen in the figure. The debug IP routing command displays routing table processes for any route, whether that route is a directly connected network, a static route, or a dynamic route. Disable debug IP routing by using either the unbug IP routing command or the unbug all command. Changing an IP address. To change an IP address or subnet mask for an interface, reconfigure the IP address and subnet mask for that interface. This change will overwrite the previous entry. There are ways to configure a single interface with multiple IP addresses, as long as each address is on a different subnet. To remove a directly connected network from a router, use these two commands, shutdown and no IP address. The shutdown command is used to disable interfaces. This command can be used by itself if you want to retain the IP address mask configuration on the interface but want to shut it down temporarily. In our example, this command will disable R2's fast Ethernet interface. The IP address, however, will still be in the configuration file, running config. After the shutdown command is used, you can remove the IP address and subnet mask from the interface. The order in which you perform these two commands does not matter. Using debug IP routing we can see the routing table process. We will delete the configuration for R2's fast Ethernet 00th interface. We can see the routing table process removing the directly connected route. The iOS also indicates that the interface and line protocol are now down. With unbug all command, all possible debugging has been turned off. To verify that the route was removed from the routing table, we use the command show IP route. Notice that the route to 172.16.1.0/24 has been removed. Warning: debug commands, especially the debug all command, should be used sparingly. These commands can disrupt router operations. Debug commands are useful when configuring or troubleshooting a network. However, they can make intensive use of CPU and memory resources. It is recommended that you run as few debug processes as necessary and disable them immediately when they are no longer needed. Debug commands should be used with caution on production networks because they can affect the performance of the device. Accessing devices on directly connected networks. To return to our configuration in the sample topology, we will now assume that all directly connected networks are configured for all three routers. The figure shows the rest of the configurations for routers R2 and R3. The output in this figure verifies that all configured interfaces are up and up. By reviewing the routing tables in the figure, we can verify that all directly connected networks are installed for routing. The crucial step in configuring your network is to verify that all the interfaces are up and that the routing tables are complete. Regardless of what routing scheme you ultimately configure, static, dynamic, or a combination of both, verify your initial network configurations with the show IP interface brief command and the show IP route command before proceeding with more complex configurations. When a router only has its interfaces configured, and the routing table contains the directly connected networks but no other routes, only devices on those directly connected networks are reachable. R1 can communicate with any device on the 172.16.3.0/24 and 172.16.2.0/24 networks. R2 can communicate with any device on the 172.16.1.0/24, 172.16.2.0/24, and 192.168.1.0/24 networks. R3 can communicate with any device on the 192.168.1.0/24 and 192.168.2.0/24 networks. Because these routers only know about their directly connected networks, the routers can only communicate with those devices on their own directly connected LANs and serial networks. For example, PC1 in the topology has been configured with the IP address 172.16.3.10 and the subnet mask 255.255.255.0. PC1 has also been configured with the default gateway IP address 172.16.3.1, which is the router's fast Ethernet 00th interface IP address. Because R1 only knows about directly connected networks, it can forward packets from PC1 to devices on the 172.16.2.0/24 network, such as 172.16.2.1 and 172.16.2.2. Packets from PC1 with any other destination IP address, such as PC2 at 172.16.1.10, would be dropped by R1. Let's take a look at the routing table for R2 in the figure. R2 only knows about its three directly connected networks. Try to predict what will happen if we ping one of the fast Ethernet interfaces on one of the other routers. Notice that the pings failed, as indicated by the series of 5 periods. It failed because R2 does not have a route in its routing table that matches either 172.16.3.1 or 192.168.2.1, which is the ping packet's destination IP address. To have a match between the packet's destination IP address of 172.16.3.1 and a route in the routing table, the address must match the number of leftmost bits of the network address as indicated by the prefix of the route. For R2, all the routes have a /24 prefix, therefore, the leftmost 24 bits are checked for each route. The first route in the table for R1 is 172.16.1.0/24. The iOS routing table process checks to see if the 24 leftmost bits of the packet's destination IP address, 172.16.3.1, match the 172.16.1.0/24 network. If you convert these addresses to binary and compare them, as shown in the animation, you will see that the first 24 bits of this root do not match because the 23rd bit does not match. Therefore, this root is rejected. In the animation, we see that the first 24 bits of the second root do not match because the 24th bit does not match. Therefore, this root is also rejected, and the process moves on to the next root in the routing table. The third root is also not a match. As shown, 10 of the first 24 bits do not match. Therefore, this root is rejected. Because there are no more roots in the routing table, the pings are discarded. The router makes its forwarding decision at layer 3, a best effort to forward the packet, but it makes no guarantees. Let's look at the second animation to see what happens if the router R2 pings the 192.168.1.1 interface on router R3. This time the ping succeeds. It is successful because R2 has a root in its routing table that matches 192.168.1.1, which is the ping packet's destination IP address. The first two roots, 172.16.1.0/24 and 172.16.2.0/24, are rejected. But the last root, 192.168.1.0/24, matches the first 24 bits of the destination IP address. The ping packet is encapsulated in the Layer 2 HDLC protocol of serial 0/0/1, the exit interface, and forwarded via the serial 0/0 firsts interface. R2 is now done making the forwarding decisions for this packet. The decisions made by other routers regarding this packet are not its concern. Cisco Discovery Protocol (CDP) is a powerful network monitoring and troubleshooting tool. CDP is an information gathering tool used by network administrators to get information about directly connected Cisco devices. CDP is a proprietary tool that enables you to access a summary of protocol and address information about Cisco devices that are directly connected. By default, each Cisco device sends periodic messages, which are known as CDP advertisements, to directly connected Cisco devices. These advertisements contain information such as the types of devices that are connected, the router interfaces they are connected to, the interfaces used to make the connections, and the model numbers of the devices. Most network devices, by definition, do not work in isolation. A Cisco device frequently has other Cisco devices as neighbors on the network. Information gathered from other devices can assist you in making network design decisions, troubleshooting, and making changes to equipment. CDP can be used as a network discovery tool, helping you to build a logical topology of a network when such documentation is missing or lacking in detail. Familiarity with the general concept of neighbors is important for understanding CDP as well as for future discussions about dynamic routing protocols. Layer 3 neighbors. At this point in our topology configuration, we only have directly connected neighbors. At Layer 3, routing protocols consider neighbors to be devices that share the same network address space. For example, R1 and R2 are neighbors. Both are members of the 172.16.2.0/24 network. R2 and R3 are also neighbors because they both share the 192.168.1.0/24 network. But R1 and R3 are not neighbors because they do not share any network address space. If we connected R1 and R3 with a cable and configured each with an IP address from the same network, then they would be neighbors. Layer 2 neighbors. CDP operates at Layer 2 only. Therefore, CDP neighbors are Cisco devices that are directly connected physically and share the same data link. In the CDP protocol figure, the network administrator is logged into S3. S3 will receive CDP advertisements from S1, S2, and R2 only. Assuming that all routers and switches in the figure are Cisco devices running CDP, what neighbors would R1 have? Can you determine the CDP neighbors for each device? In our chapter Topology, we can see the following CDP neighbor relationships. R1 and S1 are CDP neighbors. R1 and R2 are CDP neighbors. R2 and S2 are CDP neighbors. R2 and R3 are CDP neighbors. R3 and S3 are CDP neighbors. Notice the difference between Layer 2 and Layer 3 neighbors. The switches are not neighbors to the routers at Layer 3, because the switches are operating at Layer 2 only. However, the switches are Layer 2 neighbors to their directly connected routers. CDP operation. Examine the output from the Show CDP Neighbors and Show CDP Neighbors detail commands in the figure. Notice that R3 has gathered some detailed information about R2 and the switch connected to the fast Ethernet interface on R3. CDP runs at the data link layer connecting the physical media to the upper layer protocols ULPs. Because CDP operates at the data link layer, two or more Cisco network devices, such as routers that support different network layer protocols, for example, IP and Novell IPX, can learn about each other. When a Cisco device boots up, CDP starts up by default. CDP automatically discovers neighboring Cisco devices running CDP, regardless of which protocol or suites are running. CDP exchanges hardware and software device information with its directly connected CDP neighbors. CDP provides the following information about each CDP neighbor device. Device identifiers, for example, the configured host name of a switch. Address list, up to one network layer address for each protocol supported. Port identifier, the name of the local and remote port in the form of an ASCII character string such as Ethernet O. Capabilities list, for example, whether this device is a router or a switch. Platform, the hardware platform of the device. For example, a Cisco 7200 series router. CDP show commands. The information gathered by the CDP protocol can be examined with the Show CDP Neighbors command. For each CDP neighbor, the following information is displayed. Neighbor device ID. Local interface. Hold time value, in seconds. Neighbor device capability code. Neighbor hardware platform. Neighbor remote port ID. The Show CDP Neighbors detail command also reveals the IP address of a neighboring device. CDP will reveal the neighbor's IP address regardless of whether or not you can ping the neighbor. This command is very helpful when two Cisco routers cannot route across their shared data link. The Show CDP Neighbors detail command will help determine if one of the CDP neighbors has an IP configuration error. For network discovery situations, knowing the IP address of the CDP neighbor is often all the information needed to telnet into that device. With an established telnet session, information can be gathered about a neighbor's directly connected Cisco devices. In this fashion, you can telnet around a network and build a logical topology. Disabling CDP. Could CDP be a security risk? Yes, it could be. You may already have seen CDP packets in your packet capturing labs from a previous course. Because some iOS versions send out CDP advertisements by default, it is important to know how to disable CDP. If you need to disable CDP globally, for the entire device, use this command. No CDP run. If you want to use CDP but need to stop CDP advertisements on a particular interface, use this command. No CDP enable.